When engineers deploy a wireless sensor network, whether it is to monitor a dense forest for early signs of wildfires or track structural integrity across miles of aging infrastructure, they are dropping thousands of microscopic computers into the wild. In traditional IT infrastructure, networking protocols prioritize three things: fairness, high data throughput, and low latency. The goal is to move as much data as fast as possible. But in a wireless sensor network, those priorities are entirely irrelevant. The single overriding objective is energy efficiency. These nodes operate in an ad hoc configuration. They are not plugged into a wall. They do not have access to a wired power supply. From the moment they are deployed, they rely solely on a finite onboard battery. Once that battery dies, the node is permanently dead. Inside that node, the processing unit and the actual sensors use relatively little power. The true liability is the wireless transceiver. The radio draws a massive amount of current to transmit data, and it draws nearly the exact same amount of power when it is simply turned on and listening to an empty channel. Taking a standard wireless protocol like 802.11 Wi-Fi and porting it over to a sensor network is a death sentence for the hardware. To keep these networks alive for months or years, engineers have to completely rewrite the rules of medium access control. Standard carrier-sense multiple access networks, the kind your laptop uses, waste energy in four measurable ways. The first is collisions. When two nodes transmit simultaneously, their signals corrupt each other at the receiver. The entire packet is destroyed, meaning the sending node has to spend another massive burst of battery power to retransmit the exact same data. The second is idle listening. Sensor networks are designed for bursty traffic. They might wait months for a specific event, like a temperature spike, to occur. If a node keeps its radio powered on, actively listening to a silent channel for an event that hasn't happened yet, it drains its battery for zero operational gain. The third waste is overhearing. Because wireless channels are a shared medium, a node will frequently pick up packets destined for a different receiver. It spends valuable processing power decoding data that it ultimately has to discard. The final waste is control overhead. Every transmission includes metadata, headers, routing requests, and channel reservation packets. This overhead consumes transmission energy without actually moving any useful payload data. A successful MAC protocol for a sensor network must actively suppress these four specific behaviors, all while maintaining a cohesive, multi-hop routing pathway back to the data sink. The most absolute method for eliminating collisions and idle listening is to remove the element of chance entirely. This is the logic behind schedule-based MAC protocols, like SMACs and Leech. These protocols rely on time division multiple access, or TDMA. The network divides time into rigid, exclusive slots. Each individual node is assigned a specific slot. It turns its radio on to transmit or receive only during that exact window, and powers down completely for the rest of the cycle. Protocols like Leech organize this by electing a specific cluster head. This central node acts as a master clock, establishing the strict TDMA schedule and broadcasting it to all the local nodes in its cluster. Deterministic schedules eliminate collisions by design, but they have a fatal flaw. When a network is deployed to monitor rare, bursty events, the vast majority of those assigned time slots go completely unused. The network wastes bandwidth holding space for silence, and it struggles to adapt if nodes physically move or run out of battery. Strict schedules look perfect on paper, but their inflexibility in unpredictable physical environments forces engineers toward a more dynamic, contention-based approach. The Sensor MAC protocol, or SMAC, was designed as a contention-based alternative. It accommodates bursty, unpredictable traffic without suffering the massive battery drain of standard Wi-Fi protocols. It achieves this through one foundational rule: the establishment of a low-duty cycle. SMAC divides time into continuous cycles called frames. Each frame consists of a very brief active listen interval, immediately followed by a prolonged sleep interval, where the node's radio is completely shut off. This cycle repeats infinitely. By forcing the network offline for the vast majority of its existence, SMAC mathematically guarantees a massive reduction in idle listening.
But this introduces a severe routing paradox. If all the nodes are asleep at different times, how do they ever pass a message along the chain? Take a look at this diagram. It illustrates SMAC's solution, a decentralized method known as virtual clustering. Notice how the nodes group themselves by their shared schedules, Schedule A and Schedule B, rather than relying on a central master node. When a node first powers on, it listens to the channel. If it hears nothing, it generates its own schedule and broadcasts a sync packet. Any neighboring node that waking up and hears that sync packet will immediately adopt that exact schedule, creating a synchronized wave of activity. But look at the overlapping rectangle in the center. These half-shaded circles represent border nodes. They sit at the physical intersection of two different virtual clusters. These border nodes store both Schedule A and Schedule B. They sacrifice a portion of their own energy to wake up during the listen intervals of both clusters. This bridge ensures data can hop from one synchronized group to the next without breaking the chain. Virtual clustering allows an ad hoc deployment to achieve the energy benefits of a synchronized schedule, entirely avoiding the single point of failure risk of a dedicated cluster head. Even with perfectly synced listen intervals, nodes still face the third waste, overhearing. An active node will still burn battery processing data packets being sent between its neighbors. This collision avoidance scheme shows exactly how SMAC handles this. Look at the top two timelines. When a sender wants to transmit, it issues a request to send, or RTS packet. The receiver replies with a clear to send, or CTS packet. SMAC actively weaponizes these standard control packets to stealth overhearing before it starts, using a process called virtual carrier sensing. Every RTS and CTS packet contains a duration field, stating exactly how long the upcoming data payload will take to transmit. When unrelated sensors overhear either the RTS or the CTS, they read that duration. The unrelated node updates an internal variable called the network allocation vector, or NAV, with that precise time value. It then immediately shuts its radio off, entering a sleep state until the NAV counts down to 0, skipping the heavy data payload entirely. SMAC transforms network interference into a highly precise, localized energy-saving mechanism. Rigid low-duty cycles create a secondary problem, severe multi-hop latency. If a data packet has to sit and wait for the next scheduled listen cycle at every single hop along its route, end-to-end delays become unacceptable for real-time monitoring. SMAC addresses this by bending its own sleep rules, using a technique called adaptive listening. Because a node overhears its neighbor's RTS and CTS packets, it knows a transmission is actively en route. Instead of returning to its normal sleep schedule, it wakes up exactly when that transmission ends. It makes itself immediately available to be the next hop. SMAC pairs this with message passing. Instead of forcing nodes to send a new RTS and CTS handshake for every small data fragment, SMAC reserves the medium once. It executes a single handshake and then fires the fragments in one continuous rapid burst. Adaptive listening and message passing reclaim the network throughput and latency that were originally sacrificed to achieve the low-duty cycle sleep states. The design of mirrorless sensor networks forces a choice between the perfect, rigid isolation of schedule-based protocols and the synchronized flexibility of contention-based protocols like SMAC. In the physical layer of these networks, traditional metrics of raw speed and massive data volume do not matter. The only true metric of success is operational lifetime. SMAC survives by systematically hunting down the 4 sources of energy waste. Duty cycles eliminate idle listening, the NAV timer to prevent overhearing, and message passing compresses control overhead. Engineering for extreme constraints requires paradoxes. To build a robust network, you must engineer a system whose primary function is to remain asleep. Understanding these MAC layer survival tactics gives us the blueprint for the physical edge of computing. It is the underlying logic that makes planetary scale monitoring, smart infrastructure, and the true Internet of Things physically possible.